welcome back. This is Fundamentals of Micro and Nano Fabrication. This is a lecture on the module of additive processing, and we are specifically going to discuss further details of native oxide growth. So, in the previous few lectures, we went into quite some detail into the exact mechanism of how silicon dioxide is grown on silicon wafers by just providing an oxidant, either dry oxygen or wet oxidation. And in both the cases, because of the detailed differences in diffusion, solid solubility, etc., the growth rate is very different. So, wet oxidation is much faster, dry oxidation is much slower. In general, the quality of the dry oxidation is much better, the quality of wet oxidation is a little worse. So, if I were to pick up my pen, yeah. So, in general, if you were to do, if you just need a high quality dielectric, and a relatively thin dielectric, you would do dry oxidation. Typical process recipes are anywhere between 20 to 100 nanometers. If, however, you want something thicker, then you would probably want to use wet oxidation. Wet oxidation can be as thick as up to 1 micron or 1.5 micron. Any thicker, neither of these processes would actually work. You will have to look at other types of deposition techniques. One of the consequences of growing oxide on top of the silicon wafer is that you have to worry a little bit about the Pilling-Bedworth ratio. What it actually is a realization that the density of silicon and silicon dioxide is not exactly the same. Of course, atoms cannot be created or destroyed, so the number of atoms must be constant. So, if the silicon dioxide atoms take more volume than silicon, then expansion must happen somewhere. The area, of course, is constrained because you are doing the oxide growth on a wafer. The thing that is not constrained is the thickness. So, if you look at this slide, I am trying to visually show you what I am talking about. So, if you start with a silicon wafer of a certain thickness T and you oxidize and grow a certain X thickness of silicon dioxide, that silicon dioxide thickness will be a little larger than what you expect, around 50% larger. And the reason for that is the silicon dioxide atoms takes more volume than silicon atoms. And the volume growth requires that at least one of the dimensions must increase, since the area cannot change, the thickness does. The exact values can actually be calculated by looking at the molar volumes. So, the density of silicon versus silicon dioxide are given by these two numbers. The molecular weight is this. So, the number of molecules per volume can be calculated to be around 4.8 into 10 power 22 for silicon and 2.2 into 10 power 22 for silicon dioxide. If I just flip this number, then I can actually calculate the amount of volume held by 1 mole of atoms. So, Avogadro number of atoms. So, for silicon, that volume is around 12.4 centimeter cube and silicon dioxide is around 27.19. So, you can see that there is almost a factor of 2 difference here, and this factor of 2 difference then reflects in the factor of 2 increase in the effective thickness. This is important because when you are doing microfabrication, sometimes if you do not take into account this vertical increase in thickness, you are unable to fully understand the cross section that you are getting. Next, let us look at some of the equipment that is actually used to grow the silicon dioxide. I have already hinted the silicon dioxide growth is one of the most important and challenging aspects of microfabrication, at least on silicon. The silicon dioxide interface is one of the best in the world of any other material system. Its quality is what allows us to be as high, allows CMOS to be as good as it as a technology. So, how do we actually achieve that remarkable amount of purity? How do we actually achieve that remarkable amount of quality at the interface? We do that by maintaining our equipment. So, this is what the equipment actually looks like. So, this line diagram, of course, is simplifying it considerably. So, what you have is a furnace, you have a tube, and inside the tube you are vertically having these wafers, and then you are flowing whatever oxidant you want to flow. So, for dry oxygen it will be oxygen, but you also always have nitrogen. The role of nitrogen will actually be a little more clear a couple of lectures down the line, but simply speaking, it is the non-reactive inert component that allows you to control the recipe a little better and reduce defects. If you were to do wet oxidation, things would be a little more complicated. In wet oxidation, you actually have a bubbler, and in that bubbler you can fill it with ultra pure water, hopefully DI water, and then what you would do is you would bubble the inert nitrogen through this water. As the nitrogen goes through the water bubbler, it picks up some of this water vapor, and that water vapor is transported into the furnace where it actually does the oxidation. A more modern method of doing the same thing is what is called pyrogenic oxidation, where instead of having a bubbler filled with water, which can get contaminated with time, etc., you actually flow hydrogen and oxygen in an ultra pure gaseous form. And hydrogen and oxygen, of course, internally react inside the furnace to form water vapor, which does the oxidation. The important thing to, however, notice here is when you are flowing hydrogen and also flowing oxygen together, you have to be extremely careful because you are essentially creating a mini explosion. So, the electronics and the safety structures of this pyrogenic furnace need to be carefully designed. This is a little more detail into how exactly all of this happens. So, because you are so sensitive to purity and contamination is such a huge deal, this is the most sensitive step. You want your gate oxidation to be absolutely pure. So, you try very hard to remove any source of contamination or any source of irreproducibility, right. So, anything that cannot be controlled must be controlled, must either be removed or controlled. So, for example, some of the salient features you may notice is that the wafers are loaded into a quartz port. So, you cannot have, for example, a metal port or a impure glass port. It has to be an ultra pure quartz port, which is made from the same ultra pure quartz that the rest of the furnace is made of. The further things you can see is you can, for example, see a baffle here. This baffle actually allows you to reduce your heat loss and thereby maintain the temperature in the furnace more accurately, which is very important if you want to control the thickness and the quality of the oxide very accurately. Typically at the other end you have a phase seal that seals the tube so that the contamination from the atmosphere cannot get in. But however, you still need the gas to flow, so there is probably a little bit of an out and that is connected to your exhaust so that there is a continuous flow of fresh oxygen. Other than that, it is a relatively simple system with complex electronics. There are several vendors which will sell you a high quality oxidation furnace. Older models or models for smaller wafers tend to be this horizontal type of reactor. Production tools and large area wafers tend to have vertical tubes. The reason for vertical versus horizontal is purely for a space constraint. So, clean room is a very expensive real estate. So, you do not want very large equipment, and one way to save space is to, instead of have a long tube lying horizontally, just have the long tube lying vertically, and if it lies vertically it takes less space. The next thing that we would like to discuss is the growth of oxide when the oxide is extremely thin. So, we went into quite a bit of detail into the Deal Grove model where we looked at how oxide grows on the silicon, and as I discussed, it is a very elegant model. It very elegantly and very accurately explains the reality. However, the Deal Grove model does break down when you are looking at very thin oxides, or if you are looking at the oxide growth kinetics at very start of the process. So, supposing your oxidation times are either very small or your temperatures are very low, in both those cases you will grow oxides that are very thin, say something on the order of 5 to 10 nanometers. And the growth rate at these very small thicknesses often deviate from the Deal Grove model. Typically, the Deal Grove model underestimates the growth of the oxide at these very small thicknesses. This problem can be solved two ways. One is to understand what is the mechanism, and the other is to just apply a whole bunch of fitting parameters that at least accurately model the process without necessarily understanding the underlying physics. So, this is where the Massoud model was introduced and is pretty popular. Here is the equation of the Massoud model. Once again, I do not expect you to remember these formula or memorize them. However, the point here is to sensitize you that there is a problem. If you are trying to grow ultra thin oxides, you have to be a little more careful in using the Deal Grove model. The second thing to sensitize you is that the temperature dependence is very strong. Sorry, the time dependence is very strong. So, the growth rate sort of exponentially depends on time. So, very small changes on time can actually make your thickness go up and down very quickly. What this means is it is harder to accurately grow a very thin oxide layer. So, if you want to reliably grow, I do not know, 2 nanometer thick silicon dioxide day in day out, you have to be very careful in your recipe. There are several hypotheses on a physical level of why actually this happens. I do not think there is consensus or clarity on what exactly is happening in these ultra small thicknesses. Here are some of the possibilities that could be happening, but they are still open. This is still an open question in my knowledge. So, one of the things that people have proposed is that there is sort of an enhanced diffusion, that charged species form on the surface, and when these thicknesses are very small, these charged species are actually much more mobile than what a simple Deal-Grove model predicts, and that enhanced diffusion leads to enhanced growth rate. There is also an argument to be made that Deal-Grove model assumes that the oxide is growing layer by layer in a very careful fashion. That may not be the case. Initially, maybe the oxide is forming in a non-uniform fashion. So, instead of having a uniform single thickness, which allows you to use a one-dimensional model to explain everything, if you have a non-uniform thickness where some places are thin, some places are thick, then you can't actually use a 1D model. You need a more complicated model. Most of the diffusion might actually be happening through the thinner regions, and if that is the case, then the growth rate would be higher than what you expect. Also, solid solubility is a bulk concept. It does not exactly scale well. So, if you have only a few atoms on the surface, then is the concept of solid solubility even correct? Maybe the solid solubility can be artificially higher, and if the solid solubility is artificially higher, then your growth rate would also change. There are also certain mechanisms that argue that silicon substrate itself has some amount of oxygen. So, if you remember the first few lectures where we discussed substrate growth, I hinted at the fact that oxygen does exist in silicon substrate at around 10 power 16, 10 power 17 concentration, and that oxygen might play a role in growth of oxide at these very small thicknesses. Practically, this problem is handled in a simple fitting parameter type of way. So, what you actually have is this red line. So, you have a linear regime which the Deal-Grove model predicts. You have a parabolic regime which the Deal-Grove model predicts. But if you extrapolate this region, this line down to lower times or lower thicknesses, then it sort of starts deviating, and this is where you see the Masood's regime or the ultra thin oxide growth regime. However, if you are not interested in modeling accurately in this regime, what you can actually do is you can just extrapolate this red line all the way back to a fitting parameter tau, and this fitting parameter tau can then be used to fit the actual data without changing the formula that you already know. So, instead of having Tox equal to B by A into T, which is what simple Deal-Grove model predicts, you can simply do B by A into T plus tau, where tau is simply a fitting parameter. And using this fitting parameter, you can then accurately get the oxide thickness for all thicknesses above this green line. So, above this green line, the blue and the red are virtually the same. So, this is what practically a lot of the simple oxide growth models use to predict the thickness, or you can use to predict the thickness. However, ultra thin oxides are important for certain applications. One of the applications is to use them as tunneling contacts. So, I will not go into detail of what tunneling is, but hopefully some of you know that quantum mechanical tunneling predicts that if the barrier is very thin, even if it is an infinite barrier, the carriers can make their way through. So, this is what I am trying to show in this example. If the oxide is very thick and you deposit metal on two sides, the current cannot flow because the thick oxide acts as an insulator. However, if the insulator is very thin, then there is a finite probability for the electrons to make their way from left to right, and that would lead to a current. These tunneling oxides are actually very useful if you want to achieve both passivation and current carrying capacity. If this is not making sense to you, just take my word for it that ultra thin oxides are useful. In order to grow these ultra thin oxides, the oxide thickness needs to be somewhere between 1 to 2 nanometers. So, it has to be very, very thin. And in order to do that, you need to have a very precise recipe, and for those, Masood model and associated models then become extremely important. Here is an example of what you can actually expect in terms of gate current versus voltage for oxides of various thicknesses. As you can see, for small thicknesses, say 15.6 angstrom, which is 1.5 nanometers, you can actually pull in significantly large amounts of current. So, this is 10 to the power 3 amps per meter square. Another advanced concept that is worth thinking about is the issue of dopant segregation. If you would naively think about silicon dioxide growth in silicon, you would expect that the dopant in the silicon would maintain its concentration in silicon dioxide when you oxidize the surface. However, practically this does not happen or is not as simple. The details are a little complicated. In order to explain those details, I would use two concepts that you have already seen. One is the distribution coefficient K. This is something I introduced when we were doing crystal growth. K simply tells you whether an impurity would like to remain in material A or material B. The second concept I would actually use is the diffusion coefficient D. Diffusion coefficient simply tells you whether whether a certain impurity will diffuse fast or slow in a certain medium. So now, depending upon what are the values of K, the distribution coefficient, and D, the diffusion coefficient, you can actually have 4 cases. Case 1, so which is this case. So in this case, the distribution coefficient is less than 1. What that means is that the impurity would like to remain in silicon dioxide versus silicon, right? And the second thing is that this is the case where the diffusion coefficient is low in the silicon dioxide. So the impurity does not like diffusing in the silicon dioxide. So if that is the case, this is what you would expect, right? So as you oxidize silicon more and more, the thickness of the silicon dioxide increases, and at the interface, boron now has an option of remaining in silicon or remaining in silicon dioxide, and because the K is less than 1, not 1, it tries to remain in silicon dioxide preferentially and not silicon. So the silicon at the interface gets depleted of the boron, right? It gets depleted. The concentration actually falls. All this boron then accumulates in silicon dioxide. However, now it does not diffuse in silicon dioxide very fast, so it does not deplete anywhere. It sort of just keeps accumulating in the silicon dioxide and stays there. This is what happens for impurities such as boron, right? Now let's take the other example where the distribution coefficient remains less than 1. So the impurity would like to remain in silicon dioxide versus silicon. However, the diffusion coefficient is now fast. So unlike boron in silicon dioxide, which does not like diffusing, now imagine some impurity, for example boron in hydrogen ambient, where it would like to diffuse through the silicon dioxide. So when that happens, because of the distribution coefficient, you still get this depletion of dopants at the silicon surface, but those dopants do not remain in silicon dioxide. They out diffuse out from the silicon dioxide into the gaseous medium. So they just diffuse from silicon dioxide out into the gas. So now there are two pulling mechanisms, right? First, boron is going into silicon dioxide because of the K, and then further going away from silicon dioxide into the gas because of D. So this leads to severe depletion of the dopants at the interface, right? The other cases is when the distribution coefficient is more than 1. So in this case, the dopant would preferably lie in silicon and not in silicon dioxide. Again, you can take into the two cases under this sub case are when the diffusion coefficient is low, for example in phosphorus, or the diffusion coefficient is high, for example gallium. Because of the distribution coefficient more than 1, as you oxidize the surface, instead of depleting as in boron, now the dopant accumulates in the silicon, right? The dopant likes to remain in silicon more than in silicon dioxide. So your concentration actually increases as you get to the interface. However, some amount of phosphorus does get incorporated into the silicon dioxide, so you see some amount of concentration here, but whatever that concentration is can then not out diffuse because the diffusion coefficient is very low, so it just accumulates in the oxide layer. However, for the case where the diffusion coefficient is fast, for example gallium, all the dopant that is in this silicon dioxide keeps getting keep out diffusing, right? So it keeps out diffusing into the gaseous medium. So the concentration in the silicon dioxide can never be maintained. So even though the distribution coefficient is more than 1, unfortunately because there is no concentration of the dopant in the silicon dioxide, it keeps pulling the dopant even from the silicon. So unlike here where you were seeing an accumulation of the dopant, you start seeing a depletion of the dopant. So in both those three cases you see a depletion of impurities, in this one case you see an accumulation of impurities. Now why is this relevant? It is relevant because if you are starting with a uniformly doped wafer and then doing an oxidation step on it, at the interface you have changed the doping, and that how severe is that change really depends upon which dopant you are talking about and under what conditions you are processing. So, if you are not careful about these effects, you can under or over estimate the amount of dopant at the interface, which can change your device characteristics. Okay. So, always be little careful with these segregation coefficients. Okay. Further discussing more complications, and another complication is the effect of doping. So, based on the simple Deal-Grove model, you would not think that dopants would actually change anything. Unfortunately, that is not the case. At high enough concentrations, dopant tends to increase the rate at which the silicon dioxide grows. So, this is what this figure is trying to show you. So, at very high doping concentrations, if your wafer has 10 to the power 20 or 10 to the power 21 dopants, you would actually get a thicker silicon dioxide than the simple Deal-Grove model would suggest. And in fact, this enhancement or increase in the growth rate is most severe for N-type impurities such as phosphorus compared to boron. So, boron also slightly enhances, but the phosphorus and arsenic enhance significantly. So, these two curves are significantly higher. And the reasoning for that is actually very elegantly understood in terms of the simple Deal-Grove model. So, if you understood the previous slide, we discussed that the boron has a segregation distribution coefficient of less than 1, right. So, K is 0.3. So, all that boron that is there in the silicon dioxide weakens the silicon dioxide, and if the silicon dioxide is weaker, then you can imagine that the diffusion through that silicon dioxide will be faster, and the diffusion is faster, then the parabolic rate constant would be higher, but the linear rate constant would be remain unchanged, and that higher parabolic rate constant is what is causing the enhancement in the oxide growth rate. For phosphorus, things are slightly different. Phosphorus segregates primarily into silicon, so because the distribution coefficient is more than 1, so it tries to remain in silicon. However, because it tends to accumulate at in the silicon, and at the interface the phosphorus concentration grows up, that tends to enhance or catalyze the reaction between oxygen and silicon. So, if the reaction rate increases, then the linear constant would increase and the parabolic constant will remain the same, and if the linear rate increases, then again you will get an enhancement in the growth rate, and it turns out that phosphorus has a stronger effect than boron, which is what leads to that. Now, the reason these sort of details are important is supposing you had a silicon surface on which you have an N plus layer because you created a diffuse layer, and then you grew an oxide on top, and on top of that there is a metal line. Now, if you were to oxidize this wafer again or introduce oxygen into this wafer while it is hot, then this silicon dioxide layer will become thicker. And if this silicon dioxide will not just become thicker, but it will become thicker non-uniformly, because the rate of growth at the N plus region will be larger and the rate of growth in the N region will be smaller. So, this oxide will not grow in thickness as much as this oxide, and if the effect is severe enough, then this metal line might break, right, and which would cause your fabrication process to fail. So, in some of these niche areas, when you start having these weird problems, it is worth to go back at the basics and question all the assumptions that you have made in your modeling or in your process. Practically, this is what a typical oxidation recipe looks like. So, you would take a wafer, do an RCA clean, very important to do a very good RCA clean, and then you would load the wafer in nitrogen at 400-550 degrees C, ramp up the temperature in nitrogen, then introduce the oxygen for the required amount of time and temperature that you want your oxidation to be done at, turn off the oxygen, anneal for a little bit in nitrogen. The reason for this anneal we will discuss a little later when we discuss Deal-Grove model. But anyways, you would do that anneal, then you would ramp it down under nitrogen and then unload. A quick couple of slides. We have only, when in terms of native oxide, we have only discussed oxidation. Theoretically, you can even do nitridation. So, you can grow silicon nitride. It's not possible to do this simply with nitrogen, partly because nitrogen is a very inert molecule. It has a very strong bond, which means that you require remarkably high temperatures to break that bond and then form a silicon nitride, more than 1300 degrees C, which is not practical. Instead, what you can do is you can introduce ammonia, which is a little more reactive form of nitrogen, and that can form silicon nitride at temperature around 950,000 C. However, if you just look at the paper that explored this, you would see that the thicknesses that you grow are very, very small. That is because silicon nitride doesn't diffuse very well. It doesn't grow it doesn't allow for a very fast rate of growth. So practically, this is never done. If you have to grow silicon nitride, there are better ways of doing so. Finally, you can also do anodic oxidation. This is very popular for a lot of metals. However, in silicon, the oxide that you grow with anodic oxidation, which is electrochemical way of growing the oxide, is not very good. So it's rarely used in microfabrication. However, if you want a very thick layer, you may consider it. Also for gallium arsenide, you tend to form slightly better quality oxide than silicon. So for gallium arsenide, you might consider this. With that, we come to the end of this lecture. In the next lecture, we will go into a little more details of the defects that can actually form in the silicon-silicon dioxide interface. Thank you.